So I'm an agricultural engineer from LINGJUN product. So today, I'd like to talk about something we are all deeply involved in, the evolution of AI infra, the array of large models. Actually, we are in a turning point. Models are no longer just about staking parameters, and they have evolved into trillion scan spiral architecture, and MOE is no longer experimental. It's production grade. So models with tens, hundreds, or even trillions of parameters have been trained, served, and deployed into the real applications. But with this progress, has comes new challenges. As monster grows larger, training becomes more complex, and inference demands a lower latency. So how can we make our underlying system keep up? That's exactly what I want to explore today. And the next few minutes, I will talk you through this trade, architecture, innovation, and elastic operations to make this possible, from new performance to system-level intelligence. So in the past year, we can see MOE models with trillion parameter has over 100 experts. They are not a dense model like every parameter fires on every input. It only active relevantly expert per token. And it will acceleration efficiency, but also introduce new system level complexity, just like routing across hundreds of experts during training and lower latency decision making in inference. And the compute, memory, and network must be optimized. So training compute demands have increased by nearly 4 times under the comparable workload. This is not a linear scaling. So simply adding more GPU will not solve it. We need a different approach to infra design. Actually, we can see a clear difference on the training side. First is a billion parameter dense model still guiding the NLP per training. And second is the trillion parameter MOE models is going to production, such as versions of a Queen and DeepSeek. Multimodal and autonomous driving simulation also bring more complexity. On the inference side, the characteristic is even more special. Smaller dense model handle lightweight, high currency, service, and the large MOE model face challenges in routing overhead and load imbalance. Multimodal inference requires cross-modal alignment and smart caching. The point is, one cluster may run pre-training, SFT, reinforcement, and A/B testing. So it's hard for us to operating it. So our version is to break down the wall between training and inference cluster and build a uniform platform for AI workload. So LINGJUN comes. So actually, this is a cluster product, but not just another GPU pool. It's a AI native compute platform designed around the task lifecycle, built on the principle of affinity. So what do we mean about the affinity? I think we can define it bringing together the right resource into a close integration, high performance operating unit. So LINGJUN has achieved this through 4 layers of affinity. The first one is scan-up affinity. We can provide high bandwidth GPU interconnected within the instance. And the second one is scan-up affinity. RDMA high performance network enable every instance expansion up to 3.2 TB per second. We can scan up tens of thousands of GPU with microsecond level latency. And computer storage affinity, anti-interference design of the storage network, And the last one is self-healing affinity, multi-tier fault recovery from collective communications. So for example, if you want to start a 10,000 GPU task, you can set up a task group in second. And this is the true out-of-the-box really means. And now let's look at the two often overlooked but mission point, the compute storage affinity and the self-healing affinity. The first is compute storage affinity. Traditional setup on CPFS, EBS, and VPC traffic over the same NIC card. This the moment a massive checkpoint begins rating, your training job will be affected. And we have set it, we know operating like or reduce fails if even one node lags. A standard VM restart strategy will not solve it here. So LINGJUN different, we detected different. The communication patterns and applies intelligent recovery from like hot spare, soft migration, code failover, all within minutes. And we preserving topology as much as possible. So great architecture means nothing if you can't deploy it quickly. So we have here the feedback. Your technical is impressive, but I can't wait 3 days to set up a cluster. So we have optimized the deployment. Just like some method, LINGJUN now has support HP zone. The user can one-click create a ROCE-based lower latency network demands. And you can define node group from your training or inference and start a Linux 3 image with pre-install toolchains. And we support ACK integration, seamless access to a cloud-native ecosystem. The most important, a 10,000 GPU cluster can be fully configured in hours end-to-end. This was unthinkable just a few years ago. And now, whether it's emergency scaling or testing, you can get a lossless scan of testing. You can as easily as starting a container. Except for the bare metal, we have deeply integrated upstream and downstream tools, just like ACS and ACK integration with cloud-native AI inference kit. Prefilled and decode separated inference acceleration to be reduced first token latency. And in the past, training and inference is run on different clusters. If you want to train a model, exploit is pretty costly. The efficiency is really low. And now we have bring the situation. LINGJUN support uniform cluster as the 100,000 of GPU scan. You can run both massive pre-training and hand-throw port online inference. We have practiced large scan scaling, and we can reduce cross-node hop. We have achieved about 99 effective training time for trillion Prometheus MOE models. Almost no downtime due to the network failures. And look ahead. The next leap is a hypernode cluster. A hypernode is not a physical monster server. It's a logical integrated unit composed of multi-standard nodes behaving as a single high-performance unit. So what is the advantage? So in the past, the training and inference is runs on different cluster. So if you want to train a model expert for the effective cluster, and now we have breaking the situation. And the LINGJUN can support the unified cluster at 100,000 GPU, and we have participated large-scale EP optimization for MOE interference. And we can use topology-aware scaling. We can reduce across nodal hops we have achieved due to 99 effective I have introduced. And looking ahead, the next leap of the hypernode in this page. A hypernode is not a physical monster servers. We have give a lot of advantage, just like a large scaling guaranteeing with reduced fragmentation. And full mesh communication benefits out of all ops. And we can offer the flexible HBD adapter for various parallelism strategies. It's just like a NUMA computing nodes distribute scalability with the nearly single node efficiency. Of course, the root of a hypernode is still complex. So we have identified 4 challenges at least. The first one is growing deployment complexity. Shannon's law has replaced Moen's law. So performance comes from system, not insisters. And balancing the peak performance with usability, like scenarios switching hard. If you want to switch from the training to inference, you must reconfiguration, you must re-network, reinstall, and it will become too slow. And the last one challenge is stability at the scan. With tens of thousands of GPU, too much failures. So how do we reduce the downtime? So how does a hypernode actually work? It may be support flexible HBD configuration, like 4 GPU, 8 GPU, or 16 GPU. And the users can define customer policies through the console. The metadata sharing allows from between the hypernode and the child node. Your health status, your load metrics, your topology information to enable starting the scheduling. And internal is complexity, but the user's experience will be really simple. The standard cluster creation, group scaling, and configuration image rollout. But for the biggest challenge, it is still the stability. As the incorrected domains expansion, small issue can cascade. We also should implement a 3-tier handling progress. Tier 1 is how to repair. No task interruption. Tier 2 is soft migration, topology preserved. And Tier 3 can be the code failover, friendly feedback, and the goal is minute leave recovery, 0 job interruption. So finally, we can walk through the self-healing loop. When a node failed, step 1 is health check, triggers and report the status. And step 2, system analyze event and mesh scenarios. Step 3, hitting engineer decision on the how to repair if it work or not, and stop migration. And then notice the Kubernetes control panel. And step 4 is new node repaired and strongly affinity recovery. And step 5, the users can notice the loop will completely. We also provide the CMS operations platform for SRE teams to dive deep when needed. But for most users, their experience is simply, your job is keeps running. Okay, to sum up, we are undergoing a transformation in infra from raw compute to intelligent affinity system design. AI is forcing us to redefine what is usable compute really means. LINGJUN's mission is simple. make training trillion parameters models as few as easily as running a script, and make a complex MOE inference as simple as loading a web page. It is the beginning of a new chapter. So hope we can bring competitive and continuously evolving product. Thank you. Thank you for listening.